Here is now on how to obtain the single moment equation of our fourth problem using double integration method to solve slope and deflection of beams. Just like what we did on our previous problem, we will follow some simple steps in order to obtain the single moment equation of this beam. The first step is to solve the support reactions. The second step is to select a reference point where we will obtain the single moment equation. The third step is to find the segment which is farthest from our selected reference point. And the fourth step is to pass cutting plane at the segment which is farthest from the reference point. Using the left part of the cutting plane, we can obtain the single moment equation. Finally, we can draw the bending moment diagram of the beam. We will now start on step number 1. We will solve the support reactions of the beam. Usually, we have to solve first for the resultant before we can apply equations of static equilibrium summation moment at the location of support reactions. Since the resultant is just equal to the area of the uniformly distributed load, the height is equal to 20 kN per meter and the length where it is applied is 4 plus 2.5, that is 6.5 meters. So if we multiply 6.5 with 20, that is equal to 130 kN. We also solve the location of the resultant, that is at the centroid of the uniformly distributed load. Since it was applied at a length of 6.5 meters, the resultant will be located at 6.5 over 2 meters from point C and point D of the beam, and that is equal to 3.25 meters. If we now subtract the length between B to D, and that is equal to 2.5 meters, it is equal to 0.75 meters. That is the location of the resultant up to the location of the roller support at point B of the beam. If we add the distance 3.25 from point C up to the location of the resultant into 2 meters is equal to 5.25 meters. That is the location of the resultant from the support reaction at point A. We need these two distances in order to apply summation moment at point A and point B to solve for the support reactions. Applying summation moment at point B now, we can obtain this equation that is equal to 130 multiplied by its moment arm, that is 0.75. We divide by the total distance from point A up to point B, that is equal to 6 meters, and the result is equal to 6.25 kN. That is the reaction at point A. Our assumption that it is an upward support reaction was correct because 16.25 kN came out to be positive. If we now apply summation moment at point B, we can solve for the value of Vy, and that is just equal to 130, that is the resultant, multiplied by the distance, that is equal to 5.25 from the location of resultant up to the support reaction at point A. Then we will divide that by the length between point B up to point A, and that is equal to 6 meters. The result is equal to 113.75 kN. It is also an upward support reaction. We will now apply summation forces along vertical. The whole beam as our free body diagram, we can satisfy equation of static equilibrium summation forces along vertical, because we know that 16.25 plus 113.75 is just equal to 130 kN. Upward forces are equal to the downward forces. We will now proceed to step number 2. We will select a reference point where we can obtain the single moment equation of the beam. The usual reference point selected by other references like textbooks and reviewers is the left end of the beam. So I will also select point A to avoid confusion if you are using other references in learning the double integration method to obtain the slope and deflection of beams. We will now proceed to step number 3. We will find the segment which is farthest from our selected reference point at point A. But before we can do that, we have to count first how many segments does the load divides the beam into. In our case, the beam is subjected by uniform load, therefore the beam is divided by the load into several segments. The beam was also divided into several segments by the support reactions if one or more support reaction is not located at the extreme ends of the beam, that is at point A and point D of the beam. In our case, we have a support reaction located at point B and it is not located at the end of the beam at point D. Therefore, this support reaction at point B will also divide the beam into segments. In our case, the beam were divided into 3 segments, that is AC, BC, and the last one is segment BD. The segment which is farthest from our selected reference point at point A is segment BD. That is where we will pass a cutting plane. So we will now pass cutting plane A to cut that segment. We will select the left part of the cutting plane as our free body diagram to obtain the single moment equation. To those who are familiar to the bending moment diagram of the beam, here's the bending moment diagram of the beam. The three segments symbolize the three different curves, which is defined by three different equations. Because we know that at segment AC we have a first degree curve. On segment C up to point B, that is a second degree curve. And at point B up to point D, that is another second degree curve. On the bending moment diagram of the beam, so those curves were defined by different equations. But what we need is a single moment equation that can define the curve on the bending moment diagram throughout the length of the beam. That is the reason why obtaining the single moment equation is a confusing part on the analysis using double integration method to solve the slope and deflection of beams. But by using techniques and applying some consideration, we can obtain a single moment equation that can define the whole curve of the bending moment diagram of the beam. So we can now pass cutting plane A-A. Selecting the left part of this cutting plane, here is now our free body diagram. We did not select the right part of the cutting plane because what we can predict is only the equation between B and D, and it is not what we need. What we need is a single moment equation that will define the whole graph of the bending moment diagram throughout the length of the beam. At point A up to the location of cutting plane, the distance is equal to x. Since point A up to point C is equal to 2 meters, distance from point C up to the cutting plane is x minus 2. We just subtract the value of 2 meters into x. Since resultant is just equal to the area of the uniformly distributed load, the height is equal to 20 kN per meter, and the distance where it is applied is x minus 2. So we just multiply 20 into x minus 2, and that is the total value of our resultant force. And since resultant force is acting at the centroid of the uniformly distributed load with a distance of x minus 2, then therefore it is located at a distance of x minus 2 over 2 from the cutting plane, and that is also located from point C into a distance equal to x minus 2 all over 2. Since the distance from point A up to the cutting plane is equal to x, if we subtract the distance from point A up to point B into the value of a distance from point A to the cutting plane, then that is equal to x minus 6. That is the location of point B with respect to the location of the cutting plane. And that will be the moment arm of the 113.75 kN reaction at point B in upward direction. We will now write the moment equation with respect to the cutting plane. Since moment is equal to force times distance, force which is equal to 16.25 kN with the distance moment arm x, then the first term of our equation will be equal to 16.25 multiplied by x. On the second term of our equation, force is equal to 20 multiplied by x minus 2. And the moment arm is equal to x minus 2 all over 2. So that is our second term of our moment equation, 20 multiplied by x minus 2 multiplied by its moment arm, that is equal to x minus 2 all over 2. On the third term of the equation, force is equal to 113.75 kN, and the moment arm is equal to x minus 6. So here is our, we will now simplify the equation by multiplying x minus 2 into x minus 2, and here is now the result. For our sign convention, 16.25 kN will concave the beam upward with respect to the cutting plane, then 16.25, the first term of the equation will be positive, and since 20 multiplied by x minus 2 with the moment arm of x minus 2 all over 2 will concave the beam downward with respect to the cutting plane, that is a negative moment. Then for 113.75 kN, the moment arm is x minus 6. It will concave the beam upward with respect to the cutting plane, so that is also a positive moment. Bending moments that will concave the beam upward with respect to the cutting plane are positive moment, and for the bending moment that will concave the beam downward with respect to the cutting plane are negative moments. We can observe that our moment equation is valid throughout the length of the beam if we neglect the second term of the equation, that is 10 multiplied by x minus 2 squared and 113.75 multiplied by x minus 6 for x values less than 2 meters and 6 meters respectively. We can clearly understand it if we focus our attention to the cutting plane. So here's now the cutting plane. We pass the cutting plane at x is less than 2 meters, that is to the left of point C. Here is our free body diagram, and we know that the uniformly distributed load will not be included into our free body diagram if the cutting plane is passed to the left of point C. And thus, the uniformly distributed load will not contribute moment on the beam. If we pass cutting plane, which is greater than 2 meters but less than 6 meters, that is the cutting plane will be located between C and B, then the 113.75 kilonewton will not be included into our free body diagram. So here's our free body diagram. And therefore, 113.75 kilonewton will not contribute moment into the beam. As a reminder of this restriction, our mentors in engineering adopt annotation in which the usual form of parenthesis is replaced by pointed brackets. With this change in notation, we obtain a single moment equation that defines the curved moment diagram throughout the length of the beam. It should be noted that again and again, every time we perform the operation inside the pointed bracket and it will yield a negative number, then the term of the equation which contains the pointed bracket will not exist. If we will now assume values of x with the increment of 0.5 meters and substitute into the equation, we can obtain a corresponding value of m, and from that data we can be able to construct the bending moment diagram of the beam. If we now replace the value of x into 0, all the terms of the equation containing of x into our moment equation, so we can solve for the value of m at x is equal to 0, and that is equal to 0. So is negative. The second term of the equation will not exist, and 0 minus 6 is negative 6. The third term of the equation will not also exist. If x is equal to 0.5 meters, then we will replace the value of x in all the terms of the equation containing of x. So that is equal to 0.5, 0.5, and 0.5 on the first term, second term, and third term of the equation. Since 0.5 minus 2 is equal to negative 1.5, the second term of the equation will not exist. And for the third term of the equation, that is equal to negative 5.5, it will not also exist. At x is equal to 0.5 meters, m is equal to 8.125 kilonewton meter, and that is equal to 16.25 multiplied by 0.5 meters. At x is equal to 1 and x is equal to 1.5, using the same arguments, we can solve also for the values of m, that is equal to 16.25 and 24.375 kilonewton meter. At x is equal to 2 meters, so 2 meters, 2 meters, and 2 meters on the first, second, and third term of the equation. As we can observe, 2 minus 2 is 0. On the third term of the equation, 2 minus 6 is still a negative number. Since that is negative, it will not exist. So 16.25 multiplied by 2 is equal to 32.5 kilonewton meter. At x is equal to 2.5 meters, we can observe that on the second term of the equation, that is a positive number. Since 2.5 positive 0.5 meters, it means that the second term of the equation will now exist. But on the third term of the equation, since 2.5 minus 6 is negative 3.5, the third term of the equation will not again exist. So 38.125 kilonewton meter. Applying the same arguments, at x is equal to 3, 3.5, 4 meters, 4.5, 5 meters, 5.5, up to 6 meters of the beam, we can solve for the corresponding moments. That is equal to 38.75, 34.375, 25, 10.625, 8.75. So that is a negative moment. Then negative 33.125 negative moment, and negative 62.5 kilonewton meters respectively. At x is equal to 6.5 meters, we can observe that 6.5 minus 2 is positive. So therefore, the second term of the equation will exist. On the third term of the equation, we can also observe that from this time, 6.5 minus 6 is a positive number. Therefore, the third term of equation will exist at x is equal to 6.5 meters. And if we perform the operation, m is equal now to negative 40 kilonewton meter. So from x values greater than 6 meters, all the terms of the equation will now exist. 7 meters, 7.5 meters, 8 meters up to 8.5 meters, we can solve for the corresponding m, that is equal to negative 22.5, negative 10, negative 2.5, and 0 kilonewton meter respectively. So from the data above, we can now draw the graph of the bending moment diagram. So here's now the graph of the bending moment diagram. The whole graph of this equation will be defined by a single moment equation, and that is equal to this moment equation. That is what we need in solving slope and deflection using the double integration method. I hope again that you have learned from this example. To those who want the copy of this file in PDF, comment down below your email ad, like and subscribe, and I will send it to you. Thank you. Keep safe to everyone.